Hello friends, we'll see few practice problems on relations and functions today. In this video, we'll cover practice problems on Cartesian product of sets, relations, types of relations and equivalence relations. If x plus 1 is equal to 3 and y minus 2, find the values of x and y. This is a very simple concept based on ordered pair of sets. Now, it's given as x plus 1 is equal to 3 and y minus 2. As the sets are ordered pairs, x plus 1 should be equal to 3. We can simply solve this linear equation. As x plus 1 is equal to 3, we can say that x is equal to 2. Similarly, for the second pair, 1 is equal to y minus 2. As y minus 2 is equal to 1, we can say that y is equal to 1 plus 2, that is 3. So in this way, we can find out the values of x and y, that is x is equal to 2 and y is equal to 3. If the ordered pairs x minus 1 and 5y belongs to the set AB, such as b is equal to 2a minus 3, find the values of x and y. Now here it is given as b is equal to 2a minus 3. There is a set which consists of elements a and b, where b is equal to 2a minus 3. Now for the first ordered pair x minus 1, that is a is equal to x, that is first element is equal to x and second element, which is b, can be taken as minus 1. Now we know the relation as b is equal to 2a minus 3. So we'll put the values, that is b is equal to minus 1 and a is equal to x in this equation. So we can get minus 1 is equal to 2 into x. Now we need to calculate the value of x. Hence minus 1 in place of b. So minus 1 as it is, minus 1 is equal to 2 into x minus 3, that is 2x minus 3. So we get the linear equation as 2x minus 3 is equal to minus 1. That means 2x is equal to minus 1 plus 3, that is 2x is equal to 2 and hence x is equal to 1. Similarly, we'll calculate for the second pair. Again, AB is given as b is equal to 2a minus 3. Now here the ordered pair is 5 and y. So we can consider a is equal to 5 and b is equal to y. Now we need to find out the value of y. As b is equal to 2a minus 3, we can obtain the equation y is equal to 2 into 5 minus 3, that is 10 minus 3 is equal to 7. Hence y is equal to 7. So final values of x and y will be 1 and 7. If a is equal to 1 2 and b is equal to 1 3, find out a Cartesian product b and b Cartesian product a. We'll write down the given elements, that is a is equal to 1 2 and b is equal to 1 3. Now cardinality of set a is 2 and cardinality of set b is also 2. So there will be 4 elements in Cartesian product of AB as well as 4 elements in Cartesian product of BA. Now a Cartesian product B will be first element of set A and second element of set B, that is 1 1 and 1 3. Similarly 2 1 and 2 3. Similarly, with reverse order, B Cartesian product of A will be, now this one, so this 1 and 1, after that 1 and 2, then 3 and 1 and 3 and 2. So Cartesian product of BA will be 1 1 1 2 3 1 and 3 2. We'll go to next problem. If A is equal to 1, 2, 3 and B is equal to 2, 4, what are A Cartesian product B Cartesian product A Cartesian product B Cartesian product B, and A Cartesian product B intersection B Cartesian product A. Now, initially we'll write the given sets as it is. That is, A is equal to 1, 2, 3 and B is equal to 2, 4. Now, there are 3 elements in set A and 2 elements in set B. So, Cartesian product of AB as well as Cartesian product of BA will have 3 into 2, that is 6 elements. Similarly, Cartesian product of A on A will be having 3 into 3, that is 9 elements, and Cartesian product of B into B will have 2 into 2, that is 4 elements. Now we'll find out each set one by one. Cartesian product of A and B. Now set A is 1, 2, 3 and set B is 2 and 4. So Cartesian product will have 1, 2, 1, 4, 2, 2, 2, 4 and 3, 2 and 3, 4. Similarly, Cartesian product of BA. So, in order to find out the Cartesian product BA, we need to write down 2, 4 first and then set A later, that is 2, 4 into 1, 2, 3. So, we will be having 2, 1, 2, 2, 2, 3, then 4, 1, 4, 2 and 4, 3. Now, in order to find out A Cartesian product A, we'll once again write down all the elements of set A and again all the elements of set A. So, in Cartesian product of A on A, we'll be having 1, 1, 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3 and 3, 1, 3, 2 and 3, 3. Next question is, we need to find out Cartesian product of B on B. So we'll write down first set B and again set B. So Cartesian product of B on B will have 2, 2, then 2, 4, then 4, 2 and 4, 4. In order to find out Cartesian product of sets, order of the elements is extremely important. And now the last question is, we need to find out intersection of A Cartesian product B and B Cartesian product A. Now if we observe A Cartesian product B and B Cartesian product A. So these two sets we need to observe and we need to find out if there are any common elements. So we can find out 2, 2 common. After that, no, there is no other elements are there which are common. So there will be only one element in this intersection, that is 2, 2. If A is equal to 1, 2, form the set A Cartesian product A Cartesian product A. So we need to find out product of 3 sets. Now set A is equal to 1, 2. So we can simply find out A Cartesian product A as 1, 1, 1, 2, 2, 1 and 2, 2, similar to previous problem. Now we need to add one more set to this product, so we can easily obtain A Cartesian product A as, now there are already 4 elements in A Cartesian product A. So if we add 2 more elements, that is if we multiply this A Cartesian product A by 2 elements, then we will be having 8 elements. So initially to all these 4 elements we will add 1 and then we will add 2. So first of all, if we add 1 to this, then it will be 1, 1, 1. Then If we add 1 to this element, then it will be 1, 1, 2. Then 1 to 1. Then 1 to 2. Now we will add 2. So it is 2, 1, 1. Then 2, 1, 2. 2, 2, 1 and triple 2. Now here you need to understand that either you can add the element initially to the Cartesian product A, or if you are considering A product A, then you can add single element to the end of the set. Moving to next problem. If A is equal to 1, 2, 3 and B is equal to 4, 5, 6, which of the following are relations from A to B? Give reasons to support your answer. 1, 6, 3, 4, 5, 2, 1, 5, 2, 6, 3, 4, 3, 6. Then third one is 4, 2, 4, 3, 5, 1 and fourth is A Cartesian product B. Now, as A is equal to 1, 2, 3 and B is equal to 4, 5, 6. First thing we'll do is we will find out the Cartesian product of A and B. Now, A product B will be 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6 and 3, 4, 3, 5, 3, 6. Now, we'll check one by one. If at all the given elements are a subset of this Cartesian product, then that set of elements will be relation. Now, first one is 1, 6, 3, 4 and 5, 2. So, 1, 6 is there in the Cartesian product. 3, 4 is also there. 5, 2. 5, 2 is not there in Cartesian product of A and B. Hence, first set, that is 1, 6, 3, 4 and 5, 2 is not a relation. Now next question is 1, 5, 2, 6, 3, 4 and 3, 6. Now 1, 5 is there in Cartesian product. 2, 6 is also there. 3, 4, yes, 3, 4 is also there and 3, 6 is also there. That means all the 4 elements from the given set do exist in Cartesian product of A and B. Hence, given set is a relation. Now, next is 4, 2, 4, 3 and 5, 1. As 4, 2 is not there in Cartesian product of A and B, given set is again not a relation. So, from given sets 1, 2 and 3, only second one is a relation, first and third is not a relation. Moving to next problem. A relation R is defined from a set A is equal to 2, 3, 4, 5 to set B as 3, 6, 7 and 10. As xy belongs to R such that x is relatively prime to y. Express R as a set of ordered pairs and determine its domain and range. Now, we know what is prime number. Prime number is any such number which is divisible by only that number and 1. Now, in question, x should be a relatively prime to y. That means y should not be divisible by x. That is a meaning of this concept, which is relatively prime. A is equal to 2, 3, 4, 5 and B is equal to 3, 6, 7 and 10. And it's given as x is relatively prime to y. That means x should not completely divide y. That is, y should not be completely divisible by x. Now we know that if we divide, let's say just for example, 6 is divisible by 5. 6 is divisible by 2. Hence we can say that 6 is not relatively prime by 2. But if we consider the pair 2 and 7, now 2 cannot divide 7 completely. Hence we can say that 2 is relatively prime to y. Now we can find out such pairs from set A to set B. So 2, 3 can be a relatively prime. 2, 6 is not relatively prime, so will not include. 2, 7 is also relatively prime. 2, 10 is not relatively prime because 2 can divide 10 completely. Similarly, 3, 3 also cannot be included. 3, 6 also cannot be included. So we have to take 3, 7 and 3, 10. Similarly, for 4, 4, 3 can be taken. 4, 6 cannot be taken because they have 2 as common factor. 4, 7 can be taken. Again, 4, 10 cannot be taken. 5, 3 can be taken. 5, 6 can be taken and 5, 7 can be taken. So, ultimately we have found out 2, 3, 2, 7, 3, 7, 3, 10, 4, 3, 4, 7, 5, 3, 5, 6, 5, 7. So ultimately we have found such pairs which don't have any factor in common. That is ultimately they are relatively prime to each other. So R is equal to 2, 3, 2, 7, 3, 7, 3, 10, 4, 3, 4, 7, 5, 3, 5, 6 and 5, 7. So now first element from all these ordered pairs will be 2, 3, 4 and 5. Hence, domain of this relation will be 2, 3, 4 and 5. Similarly, range of this will be 3, 7, 10 and 6 is also there. So, range will be 3, 6, 7 and 10. Moving to next problem. Find the inverse relation R inverse in each of the following case. Now there are three different conditions given. We'll see them one by one. R is equal to 1, 2, 1, 3, 2, 3, 3, 2, 5, 6. R is equal to xy such that xy belongs to n and x plus 2y is equal to 8. R is a relation from 11, 12, 13 to 8, 10, 12 defined by y is equal to x minus 3. Now, suppose in any relation, if element A is related to element B, then in inverse relation, that is in R inverse, we can say that if R is equal to A related to B, then R inverse will be B related to A. So, in first problem, when R is equal to 1, 2, 1, 3, 2, 3, 3, 2 and 5, 6, simply R inverse will be having all these elements but in reverse order. That is 2, 1, 3, 1, 3, 2, 2, 3 and 6, 5. Now in next question, R is equal to xy such that xy belongs to n and x plus 2y is equal to 8. Now initially we'll solve this equation, that is x plus 2y is equal to 8. So if we simplify, x will be equal to 8 minus 2y. Now one more condition is given as xy belongs to n. That means x and y can have values from 1, 2, 3 up to infinity. Now let's suppose if y is equal to 1, then we can calculate x as 8 minus 2 into 1, that is 6. Similarly, for y is equal to 2, we can calculate x as 8 minus 2 into 2, that is 8 minus 4, we can get 4. Now, if y is equal to 3, then x will be equal to 8 minus 2 into 3, that is 8 minus 6 is equal to 2. Now, if y is equal to 4, then x will be equal to 8 minus 2 into 4, that is 0. But our condition is x and y belongs to natural number. So, we cannot have any value which is equal to or greater than 4. Hence, y can have only 3 values as 1, 2 and 3, for which we will get x as 6, 4 and 2 respectively. Hence, we can define r as 6, 1, 4, 2 and 2, 3. and hence our inverse will be equal to 1, 6, 2, 4 and 3, 2. Now we'll move to third case. R is a relation from 11, 12, 13 to 8, 10 and 12 defined by y is equal to x minus 3. Now for the first element x is equal to 11, y will be equal to x minus 3, that is 11 minus 3 is equal to 8. Now for the second element x is equal to 12, y will be x minus 3 as in 12 minus 3 which is equal to 9. But if we compare this 9 to given elements of y, then initially for x is equal to 11 we have got y is equal to 8. 8 belongs to the given set of y. But for x is equal to 12 we are getting y is equal to 9 which doesn't belong to the set y. Hence, we cannot consider this pair as 12 and 9. Moving to third one, x is equal to 13, y is equal to x minus 3, that is 13 minus 3 is equal to 10. Again, 10 is already there in set y, so we can consider the value 13 also. Hence, we can define r as first value, that is 11 and 8, and second value is 13 and 10. Hence, r is equal to 11, 8 and 13, 10, and hence r inverse will be equal to 8, 11 and 10, 13. Understood? Moving to next question. Write the relation r is equal to x cube such that x is a prime number less than 10 in roster form. So right now the set relation r is given as x cube such that x is a prime number less than 10 and we need to write this relation in roster form. R is equal to x cube such that x is a prime number less than 10. Now we know that there are 4 prime numbers which are less than 10, that is 2, 3, 5 and 7. Now we know that 2 cube is 8, 3 cube is 27, 5 cube is 125 and 7 cube is 343. So we can write down r as 2 related to 8, 3 related to 27, 5 related to 125 and 7 related to 343. So there will be 4 pairs in relation r as 2, 8, 3, 27, 5, 125 and 7, 343. Again, it's a very simple problem. Moving to next problem. Let A is equal to 1, 2, 3, 4, 5, 6. Let R be the relation on A defined by R is equal to AB such that AB belongs to A and B is exactly divisible by A. Now we have already solved one problem where y was relatively prime to x. Now similar kind of concept we need to use here. Now here also it is given as AB belongs to A as well as B is exactly divisible by A. We need to write down this relation R in roster form as well as we need to find out domain of R and range of R. Now A is given as 1, 2, 3, 4, 5 and 6. So the first element we know that every element is divisible by 1. So while writing this relation R in roster form, initially we can write all the elements as 1, 1, 1, 2, 1, 3, 1, 4, 1, 5 and 1, 6. Now after that we know that 2 cannot divide 1 completely. So we cannot consider 2, 1. Similarly we cannot consider 2, 3 also. But 2, 2 we can consider because 2 can divide itself completely. Besides 2 can divide 4 also completely, 2 can divide 6 also completely. So after initial 6 element, that is 1 1, 1 2, 1 3, 1 4, 1 5 and 1 6, we need to move on to 2, that is 2 2, 2 4 and 2 6. Now for 3, we can have 3 3 and 3 6. Now for 4, we can have just one pair, as in 4 4. For 5 and 6 also only one pair, that is 5 5 and 6 6. So ultimately our relation R will contain elements as 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 2, 2 4, 2 6. After that 3 3, 3 6 and 4 4, 5 5 and 6 6. So domain of R will be 1 2 3 4 5 and 6, and similarly range of R will be 1 2 3 4 5 and 6. So ultimately in this case domain and range is equal as 1 to 6, which is again equal to set A. Moving to next problem. Let A be the set of all human beings in a town at a particular time. Determine whether each of the following relations are reflexive, symmetric and transitive. R is xy such that x and y work at the same place. Now we'll check whether this relation R is a reflexive relation or not. Now let's suppose x is any arbitrary element of R. So if x belongs to R, that means x and x work at the same place, which is always true. As in, if x is working at some particular place, so obviously x is working at that place. Hence, x and x work at the same place is always true because they are same. Hence, x belongs to R, and hence we can say that this relation R is a reflexive relation. Now we'll check whether it is symmetric or not. Now let's suppose there is one pair as xy which belongs to R. That means x and y work at the same place. Now when we say that x and y work at the same place, so obviously y and x are also working at the same place. Hence, if xy belongs to R, we can always say that yx also belongs to R, and hence R is a symmetric relation also. Now we'll check whether this relation is transitive or not. Now let's suppose if xy belongs to R and yz also belongs to R. So ultimately what it means is, when xy belongs to R, x and y also work at the same place. Similarly, it's also given as yz also belongs to R. That means yz also work at the same place. Now let's suppose x and y work in some company and y and z also work in the same company. So obviously we can say that x and z are working in the same company, and hence x and z also belongs to R, and hence we can say that this relation is also transitive. So R is equal to xy such that x and y work at the same place. This relation is always reflexive, symmetric and transitive. We'll check the second scenario. R is equal to xy such that x and y live in the same locality. Now this condition is exactly similar to the previous condition. So let's suppose if x is an arbitrary element of R. Now x belongs to R. That is given that x and x live in the same locality. So suppose x is living in some locality, let's say in Pune. So ultimately when x is living in Pune, obviously x is living in Pune. So x is always a reflexive relation. Now we'll check whether it is symmetric or not. Now let's suppose if x and y belongs to R, that is x and y live in the same locality. As x and y live in the same locality, we can also say that y and x also live in the same locality. So when xy belongs to R, we can always say that yx also belongs to R, and hence R is a symmetric relation. Now we'll check whether it is transitive. Now, similar to the previous condition, let xy belongs to R and yz also belongs to R. So ultimately, x and y are living in some locality and y and z are also living in the same locality. So obviously we can say that x and z are also living in the same locality, and hence xz also belongs to R. So as xz also belongs to R, we can say that R is a transitive relation, and hence this relation is reflexive, symmetric, as well as it is transitive. Now we'll check the third scenario. R is equal to xy such that x is a wife of y. Now check this scenario carefully. Let's suppose x is any element of R, that is x is a wife. Now in the given relation it is given as x is a wife of y. Now x cannot be wife of itself, that is x cannot be wife of x is obviously not true. Hence xx doesn't belong to R, and hence this relation R is not reflexive relation. Now if xy belongs to R, that means x is a wife of y. Now x is a wife of y, that means x is a female and y is a male. So y cannot be wife of x because y is a husband of x. Hence once xy belongs to R, we cannot say that yx also belongs to R, because when xy belongs to R, obviously yx will not belong to R. Hence this relation is not a symmetric relation. Moving to third condition of transitivity. Let xy belongs to R and yz also belongs to R. Now what do you mean by xy belongs to R is a x is a wife of y. Similarly, if yz belongs to R, then we have to say that y is also wife of z. Now initially x is a wife of y, that means x is wife and y is husband. So our assumption itself is not true, because now if we say that yz also belongs to R, then y has to be wife and z has to be husband, which is not true. Hence this relation is not transitive also. Hence in this case R is not reflexive nor symmetric, and it is not transitive also. We'll check the fourth scenario. xy such that x is a father of y. Now let's suppose x is any arbitrary element of x. So once we say that x is arbitrary element of x, that means it will fulfill the given condition. So is it possible that x is a father of x? No, it is not possible. Hence x cannot be the element of relation R. Hence it is not reflexive relation. Now let's suppose we'll check the relation for whether it is symmetric or not. Now let's suppose xy belongs to R. What do you mean by this xy belongs to R is x is a father of y. Now once we say that x is a father of y, that means obviously y is either son or daughter of x. So we cannot say that y is a father of x, because y is either son or daughter of x. Hence when xy belongs to R, we can obviously conclude that yx doesn't belong to R. Hence it is not a symmetric relation. Now we'll check for transitivity. Let's suppose xy belongs to R and yz also belongs to R. xy belongs to R, that means x is a father of y. So x is a father of y and yz also belongs to R. That means y is a father of z. So once x is a father of y and y is a father of z, that means x is grandfather of z. But in order to fulfill the condition of transitivity, x should be father of z, which is not true because in this case it's coming as x is a grandfather of z and hence R is not transitive also. So x is a father of y. This relation is not reflexive, it is not symmetric and it is not transitive also. Moving to next problem, check whether the relation R defined on set A is equal to 1, 2, 3, 4, 5, 6 as R is equal to AB such that B is equal to A plus 1 is reflexive, symmetric or transitive. Now A is equal to 1, 2, 3, 4, 5 and 6 and it's given as R is equal to AB such that B is equal to A plus 1. That is B is equal to A plus 1. So it's given as A is equal to 1, 2, 3, 4, 5, 6. That means A can take any of the 6 values, that is 1, 2, 3, 4, 5 and 6. So for all these values of A, we'll calculate the value of B. So suppose for A is equal to 1, then B will be equal to A plus 1, that is 1 plus 1 and hence B should be equal to 2. For A is equal to 2, similarly B will be equal to 3. For A is equal to 3, B will be equal to 4. For A is equal to 5, B will be equal to 6. For A is equal to 6, B will be equal to 7. But this 7 does not belong to A and hence we cannot take this value as A is equal to 6. So relation R can have these 4 pairs as in 1, 2, 2, 3, 3, 4 and 5, 6. Hence, we can define the relation R such as R is equal to 1, 2, 2, 3, 3, 4 and 5, 6. Now, in this relation, R does not contain any of the element which is related to itself. Hence, this relation is not reflexive relation. Now, we'll check whether this relation is symmetric. Now, let's suppose if we consider first pair, that is 1, 2. Then reverse order of this 1, 2 will be 2, 1. So, for this pair 1, 2, there don't exist any element as 2, 1. Hence, it is not symmetric also. And now for transitivity, we can observe that there is a pair of elements, that is 1, 2 and 2, 3. But 1, 3 is not there. Hence, this relation is not transitive also. Moving to next problem, show that the relation R on set Z of integers given by R is equal to AB such that 2 divides A minus B is equivalence relation. Now in this problem there are two concepts which are used. First is integers. Integers means all the numbers which are negative numbers as well as positive numbers and 0. And one more concept is used as an equivalence relation. What do you mean by equivalence relation? Equivalence relation is any relation which is reflexive, symmetric as well as transitive. R is equal to AB such that 2 divides A minus B and this R is defined on set of Z. Now this AB can have values of all the integers, that is negative numbers 0 as well as positive numbers, such as difference between AB should be divided by 2. Now if we want that this difference should be divisible by 2, that means the difference should be even number. So we can find out relation R such as -3 -1. Now here difference is -4, or 0 2 difference is +2, 4 2 1 1, etc. That means we can have the difference as at either negative even numbers, positive even numbers, or 0. So all such pairs can be there in this relation where difference can be negative even number, 0, or positive even number. Now, we need to prove that this relation is equivalence relation. So, first of all the pairs which can give you difference 0 will be divisible by 2. As in, because 0 can be divisible by 2. So, we can say that this relation is a reflexive relation. Hence, any element AA can be there in this relation. Now, AB and BA will give you the same difference just with opposite sign. But this difference will always be divisible by 2. Hence, the given relation will be symmetric also. Now, we'll check whether it is transitive or not. Now, once we say that AB belongs to R and BC also belongs to R, that means we can always find out that AB belongs to R, that means difference B minus A is divisible by 2. Similarly, BC belongs to R, that means C minus B is also divisible by 2. Now, if we find out the difference of C minus A or A minus C, then this difference will also be divisible by 2. Hence, we can say that AC also belongs to R, and hence this relation is transitive also. Now, as this relation is reflexive, symmetric as well as transitive, we can say that the given relation is a equivalence relation, and hence it is proved. Moving to next problem. Let R be a relation on set A of ordered pairs of integers defined by xy relation uv if xv is equal to yu. Show that R is an equivalence relation. Now, it's given as relation R on integers, that is relation R on Z Cartesian product Z is defined by xy relation uv such that xv is equal to yu for all xy and uv belongs to Cartesian product of Z. Now we'll check whether it is reflexive or not. Now let's suppose for any x and y which belongs to Z Cartesian product Z, obviously we know that xy is always equal to yx. Hence xy relation xy is always true, and hence xy relation xy for all xy belongs to Z Cartesian product Z, and hence this relation is always reflexive. Now we'll check whether it is symmetric or not. Let xy and uv belongs to Z Cartesian product Z such that xy relation on uv, then we can say that xv is equal to yu, which implies that uy is equal to vx. So we can also say when xy is related to uv, we can also say that uv is also related to xy, and hence this relation is symmetric on Z. Now we'll check whether it is transitive. Now let's suppose xy, uv and ab belongs to Cartesian product of Z such that xy is related to uv and uv is related to ab. Now once we say that xy is related to uv, that means xv is related to yu. Similarly, uv is related to ab, that means ub is related to va. So now if we consider product of these two, then we can say that x product of LHS, that is xv into ub will be equal to yu into va. So if we cancel the related terms, then we can say that xb is equal to ya, and hence xy is related to ab, and hence r is a transitive relation on z. Now we have already proved that this relation is reflexive, symmetric as well as transitive, and hence this r is an equivalence relation on z. That is proved. So in this video we have seen practice problems on Cartesian product of sets, relation, types of relations and equivalence relations. Thank you.